floor. Thank you.
Okay, thank you for the organizers for putting up this very timely conference in this very special location. So I can hardly work in my hotel room because the view is so amazing from there. But I managed to finish my talk anyway. So I will start very slowly, so this will be boring for some of you who know already very much about quantum geometry, but maybe there are some people in the audience who don't know, so you have to time to catch up. And unfortunately, I missed the first day, so I might repeat some stuff, but I can't help that. Then I go to more technical things. I will look at rhombohedral graphite from the quantum geometry perspective. And then superconducting transport in flat bands, what can be new there, what can come from the flatness and so on, and from quantum geometry again. And finally, then look at what quantum geometry, how it affects pairing. So let's start from the basics. So quantum geometry is kind of old stuff from the 90s when people used it to describe, for instance, how to make optimally localized one-year functions and so on. So that's where things started, and then quantum information also benefited from that. But then around, let's say, 2013, 15, 14, there were a few works, and one was ours, about superfluid weight, saying that quantum geometry can be actually important for some many-body physics or other band physics phenomena. And then since then it has kind of exploded, so you see these very recent findings of a lot of context where quantum geometry matters. And if you are interested, there are some review articles available. So to set the basics, quantum geometry can be described by so-called quantum geometric tensor, which you get in this way if you are interested what is the distance between quantum states, defined like this. So this is the wave function parameterized by some thing. You can think this is the Bloch function at the momentum, lattice momentum if you want concreteness. And you can describe the infinitesimal distance like this. Here is the changes in k and something, and that something should be a metric. And if you introduce a Gates invariant version of that, like this, here, it turns out that there is a more general concept called quantum geometric tensor, which involves derivatives of your wave functions and some projectors, and its real part is this quantum metric that describes the amplitude distance, and the imaginary part is related to phase distances, and it's the Berry curvature. So that, of course, then connects to topology. So somehow quantum geometry is perhaps the bigger context, and topology is part of it. And then a cartoon to really understand what is going on for those who are not yet experts. So think, for instance, that your eigenstates are formed in a periodic system like this. You would get bands, but now your unit cell can have additional degrees of freedom. It can have many orbitals, or maybe your system has some spin or polarization degree of freedom or something. And then your bands can be either composed of one orbital or one polarization, or they can be hybridized. And if it's only one orbital content, then if you change the wave functions a bit, you stay in this space of AB Bloch sphere on the same position more or less, so you have no distance between the states. While if now you have hybridized bands, then if you change a bit the wave function, you might change the AB alpha beta content here, and you move on the sphere at a finite distance, so you have finite metric. So it tells how hybridized your bands are with orbitals or in some other quantity. And why this would be important for many things? Well, this is just one example, but it's very illustrative. Look at the current operator. So that's defined like this. These are the periodic part of the Bloch function. You take the expectation value, or this matrix element, and this is the current operator position here, and position is derivative of the momentum. So that's why you will have these derivatives of the wave functions appearing in things like current. Of course, there is another thing which is maybe more kind of intuitive or familiar. The dispersion comes, it affects your currents, but there are always these kind of things in multiband systems. When you have this M and N have to be different for this to be non-zero. So basically, whenever you have the electron position and you have multiband system and so on, you will get matrix elements which somehow connect to quantum geometry. So it's everywhere. But of course the question is like, is it kind of a useful thing to look at these things from the quantum geometry perspective? I think it is. I will tell you later why. But recently people have got interested in measuring this quantum geometry. Yep.
This is a basic question, but any material, it's never going to be a single orbital or a single atom, right?
Yeah. Yeah.
So how do you distinguish, or maybe you don't, I don't know, something that is trivial for non-trivial? Because I assume that you always must have something, right? So
Yeah. But it depends, like, then how strong this orbital hybridization is in your band. So even if you always have multiple orbitals, it could be that sometimes some band is mostly from one orbital, or the change to the other orbital is very slow, and then these quantum geometry effects are small. So yes. It's quantitative in real materials. Of course, in our toy models, it can be very qualitative, because people just assume, okay, it's single band Hubbard, and you throw away a lot of things. No. I would say that it's trivial. Quantum geometry is trivial when both G and Berry curvature are zero. So because there are systems where even the Berry curvature is zero, but quantum geometry is still non-zero, and I would call that quantum geometrically non-trivial. But of course, then topologically trivial or non-trivial is another thing. There you have to have Berry curvature and integrate it to add up something. No, not at all. Yeah. When it's topological, it's always quantum geometrically non-trivial, but not the other way around. Okay. So these are some of the first experiments that measured both quantum metric and Berry curvature, and this was typical in optical systems, where you have the orbital degree of freedom is actually polarization. So it's easy to do measurements, not so easy, but possible. This is from my group, because we also do experiments, and then some artificial quantum systems. But recently there are some measurements also in materials, real materials where you have just essentially two orbitals, so you can do some kind of orbital resolved ARPES, and from there you can get it. And then very beautiful photonics experiments where they use SLMs to block some orbitals and get these things. So it's a possible thing to measure. But now let's go to why it would be interesting, and in yeah. Yeah, because the integrated quantities are easier to measure. They appear in many responses, but this is really K-resolved all over the Brillo. So yes, so one of the things why I think this is a useful concept is that it somehow quite beautifully solves one puzzle in superconductivity, like why can there be superconductivity in a flat band where electrons are localized? But let's go to that. And why we are interested in flat bands? Well, because they are there. You know, you all work on some twisted or other flat band systems. So you have superlattice, and this flattens the band. And you can also have special geometries like the lieb, where where you can have wave functions that have plus and minus amplitudes, and then by destructive interference you get localization into this bracket. And then of course Landau levels. So this is one motivation to look at flat band superconductivity, but other one is that obviously if there's no kinetic energy, interactions dominate. So maybe you get superconductivity very easily. And indeed, if you do simple BCS calculation, you see that in a flat band, the critical temperature becomes linearly proportional to the interaction, attractive interaction, and volume of the flat band, and that's of course much better for small interactions than this usual exponential suppression of BCS theory. So that looks good. And by the way, by flat band we mean something where the bandwidth is smaller or even similar than the, well, let's say, a bit smaller than the interaction. So it doesn't need to be exactly flat. So this is an argument about the absolute value of the order parameter, so the bearing gap. But of course, in superconductivity, you need to have Meissner effect, and for this you need finite superfluid weight, this quantity. This is very different from usual current, so it has to be a perfect diamagnet, and that quantity is essentially like the inverse effective mass of a Cooper pair, because Cooper pair motion is given by the phase of the order parameter if it spatially varies, and the free energy change when you have supercurrent looks like this. So this ds appears there, and it's the inverse of penetration depth. So this thing should also be non-zero. And the problem in a single band or continuum in conventional BCS theory is, when we think about flat band, and is given by the Cooper pair density divided by effective mass, and this is 0 in a flat band. So it looks like, okay, a bad ending to our good story, but this is of course just a single band result. And if you do carefully the multi-band theory, then we found out that actually there is there are two contributions to superfluid weight or stiffness. Other people use that language. So this this usually appreciated component, which is proportional to the derivative of dispersion, and then another part which is non-zero only when there are multiple bands, and it can be non-zero in a flat band. And we call it geometric because under certain conditions it's proportional to the quantum metric. And here a kind of disclaimer that this does not of course tell that, okay, every time you have a quantum metric you have superconductivity, because it's always a competition of orders. So you need to have strong enough attractive interactions for superconductivity to win, because the same argument actually stabilizes also magnetism in flat bands. But sometimes the attraction can win. So to see this quantum geometry more clearly, let's look at one specific approximation or limit. Isolated flat band. This means that the interaction is bigger than the bandwidth, so that you are in a flat band limit, and the band is isolated, that the band gap to the next band is bigger than the interaction. And furthermore, we assume uniform pairing, meaning that the pairing gap is the same in all orbitals where it's non-zero. And that actually happens in systems where the orbitals are related by symmetry, so it's not like totally ridiculous assumption. And in this case you can derive nice analytical formulas. The superfluid weight, this is now a completely flat band. You have only this geometric part which is directly linearly proportional to interaction, so this scaling, linear scaling is there as well. Filling, so nu is filling, so maximize that half filling, number of orbitals. And then this is the integrated quantum metric. So integrated over Brillouin zone and the minimal value of that. So these formulas were basically derived in our early work, 2015, but then in this work involving Kukka, Huhtinen, and Andrei, and Jonah, we showed that actually you have to take the minimal version of the quantum metric. And that's a very subtle thing, because quantum metric and Berry curvature, they are so-called orbital embedding dependent. They depend on where you place your orbitals, if you keep the hopping change, but change the positions. And this is known already for some time, but superfluid weight doesn't depend on it. So there was kind of a discrepancy, and it was solved by this minimal quantum metric concept. Yep.
So if I have new big 21, so the band is very empty.
Yeah.
Going to have some superfluid weight.
Mm-hmm.
And it's going to be proportional to the integral of the quantum geometry over the entire band.
Yeah.
Even though I feel only a very small part.
Yes, yes.
Is there a simple way to understand it?
Well, I mean, in BCS theory, all the particles are, all the k-states are kind of involved in the, this is flat band physics. Because, if you think about dispersive band, you think that the k values around some Fermi level and so on are more important. But in flat bands, all k states are the same. So that's why it becomes like this.
So if you look at the rotation of the function of momentum,
yeah, it's a constant. Yes. Yeah. Yeah. Mm-hmm.
This is basically how stable.
Yeah.
That superconductivity is bipolar.
Mm-hmm.
That's all this also bipolar. Conventional BCS or BCS bipolar.
Yeah, the general argument that there are these geometric and conventional, but this is valid pretty much for anything, because it's just saying that, hey, you have to look at the interband contributions as well. So I'm sure it's there. This simple formula here, this you can derive only in with on-site interaction, simple thing and so on. But in general, the geometric contribution should be there.
Can I take the prerogative of this was one question?
Yeah.
Sorry for so many questions, but it's very nice. So presumably your M, that's coming from the other bands that are around.
Yeah.
So that M element should also depend, I presume, on the energy difference between where your flat band is located and the other bands. So if I were to take the limit where this, if it's almost never possible, but if I were to take a limit that this separation goes to infinity, what will be your answer?
Yeah, I mean, this is isolated flat band limit, so in some sense I have already taken it to infinity. But now you have to think that you have many bands, and if you calculate the Bloch functions of all bands, there is something like a completeness relation. So no matter how far the bands are, the Bloch functions are always related. Of course, if the bands are very far, then the other bands, then this hybridization that I had in my cartoon, this becomes smaller and smaller. So there is no, I mean, the other bands are always involved, but if you take them very far away, this hybridization goes away, and then this goes towards zero. Okay, so then some intuition about this, why there can be this kind of contribution. So in this picture, you can think about first a trivial flat band, like just electrons localized at atomic limit, and no overlap in the one-year functions. So then if you introduce interactions, nothing happens. But now when we have these non-trivial flat bands like Moire or Lieb lattice or whatever, you have flat bands due to destructive interference, so you can actually have one-year function overlap. And then when you introduce interactions, there can be currents. And to obtain this insight, there was, I acknowledge collaboration with Sebastian Huber, because we mapped this thing to a spin model where we directly see that the Cooper pair motion is related to overlaps of neighboring orbitals. And this connects then to topology and quantum geometry, because it's well known that topology and quantum geometry control how localized one-year functions are. And this is then understandable that one can derive this kind of bound that we had in our early paper, that if you have a topological system, then it would have a finite superfluid weight, even in flat band. Okay, so this was, we started this well before TBG, but then it came and suddenly people thought that this might be actually relevant for something. And by now there are experiments who try to probe this. So they have measured in these two papers the superfluid weight, here directly as an inverse of kinetic inductance, and here somehow indirectly. Both see this kind of dome as function of the filling. And now this simple naive single band PCS formula with the real effective mass of the band would give something very, very small. So there must be something else. And here, for instance, they made some kind of scaling with the gap that kind of matches. So also our theory shows that the superfluid weight should mainly scale as the gap. So this quantum geometric contribution is a possible explanation for this observation, but I think this still needs more detailed theory. But it's very interesting. Okay, so that was the introduction. And now I go to rhombohedral graphite, which has been covered many, many times already in this conference, but we wanted to look at it from the quantum geometry perspective. And this is work of Kuodongyan and Tero Heikkilä and me in archive. So this slide is maybe not needed here, but okay, this is the structure. And if you take the main hoppings, the intra and interband, the Hamiltonian is simple. It has nodes, and these nodes make this kind of spiral in K-space. And if you project it to the surface bands, you see that the surface bands are kind of flat. And of course, this is a very popular system. There are superconductivity reports coming so much that I have to use very small fonts to get something else on the slide as well. So people have tried to describe this. One option is, okay, it looks like SSH model. You can do that, but it actually describes only one point in the K-space. And then one is missing something, because for instance the decay length of the surface states into the bulk, that's K dependent, and this model doesn't take it into account. But then there is much better, this two orbital effective model, where the bulk is kind of projected to the two orbitals at two surfaces, and this one gives good dispersion in the center of K-space and good quantum geometry also in the rim, but it's not topologically correct. So we compare here, we now calculate the quantum metric for this model. So introducing a small surface potential so that we open the gap between the two surface states. So here is the surface potential, and the full model gives this kind of quantum metric for different number of layers, these peaks. And when we increase the surface potential, it changes a bit, but essentially the same. And the big difference to the two orbital effective model is that here you have zero quantum geometry in the middle, while in this full model it's non-zero. So this is now essential for us. So this up for the valence band for the upper one. So these are the basic features of quantum geometry. It's non-zero at center and peak at the rim, and of course it converges to an infinite result. It's scaled with, yeah, it's just the Brillouin zone of the, here you have to define the unit cell, oops. Yeah, it depends on how many layers the unit cell kind of grows. But here, for instance, it would be this. Yeah, okay, this is the scaling of K, yes. So this one, gamma 1 divided by, yes. But the Brillouin zone or unit cell is defined by the size, but the scaling is different. Yeah, so then we can look at the n equals infinity limit, and there one can write explicitly the surface wave function. And it looks like this, and here is the decay length. So the decay of the surface state into the bulk. And now we can calculate the quantum geometric tensor, which has now both the metric and the Berry curvature. It looks like this. And this was also obtained by Andre in this paper where I don't know, he calls it Berry Trascant in honor of Sir Michael. And this thing, why we get now a finite quantum metric here is very different from what I talked before, because it actually comes from the momentum dependence of this decay length or decay momentum. So the momentum dependent decay of the surface state gives you quantum metric. And this, for instance, these simple models miss this thing. And yeah. So yeah, so then this is really at the surface, then it doesn't let me yeah, so then it doesn't penetrate at all. Yeah. Yeah. Yes. Yeah, so this is log and in the power. So it when K grows, it penetrates more into the bulk, and then the 0 point kind of not at all. Yes, okay, so then we can understand these peaks, where they come from. So as you see, they move as function of n, the layered number. So this is because at certain point in K, the penetration or the decay length becomes the same as the number of layers. So you kind of connect the surface and the bottom bands, you hybridize them, and then you get a big quantum metric, because it's always coming from hybridization. So this kind of formula. But in the center, there is no n dependence and there is no surface hybridization. So K equals 0, they really stay at the two surfaces. So now in quantum geometry there exists this kind of trace condition, that the trace of the metric is always bigger than the Berry curvature. And if you now look at this quantum geometric tensor of rhombohedral graphite and compare it to the Landau levels, we see that it's very, very similar. So for Landau levels, this is the geometry, and for the 0, you see it's exactly like this, up to the factoring front. So the two surface band of rhombohedral graphite, they are like decoupled Landau levels, lowest Landau levels with opposite B fields. Yeah, but let's say in the middle, when k equals 0, they are very, very similar. Yeah, and then for higher k, this just goes, it changes, there are these peaks and so on. But I mean the center area, it's the same. And in Landau levels and also here, this trace condition is saturated, so this we can call as ideal quantum geometry, which is important in some other context too. So then, this was all for the simple model where we have two hoppings, but let's introduce all the realistic ones, and then the band structures change, as you know. But then when we have a displacement field, you get more and more polarized, either to the top or top or bottom band, top or bottom surface, and then after a certain, let's say, critical value of displacement field, you are more or less polarized, and at that point, then this quantum geometry is what I just described. So even in the realistic scenario, if you have a displacement field, we can have this ideal quantum geometry stuff. And then what does it mean, all this for superconductivity? So first of all, this is not quantum geometry thing, but just the surface polarization thing. So if you look at in the orbital basis, the order parameter, then if you polarize to one surface, you effectively double the coupling strength. And that then, if we are in some kind of weak coupling scenario, can be a big effect. And we propose that this superconducting dome SC1, which is S-wave, believed to be S-wave and not so maybe highly strongly correlated and so on, that it appears when the displacement field is sufficient to really polarize to one of the surfaces. And we looked at the values in our calculations, and they match. Okay, but then to the since we have calculated quantum metric, so can we now separate the geometric and conventional parts in this case? And of course, yes, we can. Here they are, how they look like. And now in the picture, okay, first of all, if we think that the order parameter is already fully polarized, there is even a very nice analytical formula for the geometric part. And here is a picture how things look like. So first, the order parameter is this thing. So it's obviously highest in the middle. And then the quantum metric diverges here at the rims, both for the geometric and conventional parts. That's because the surface band's hybridized there. But there is also finite geometric superfluid weight in the middle. So also this flat part can carry some supercurrent. And this really comes from the quantum geometry that was the k dependence of the decay length. Yeah. Sorry, yeah, PK, sorry, this I didn't explain. That's a projector to the valence band. So it just contains the Bloch functions. It's a projector to a band. Sorry, yeah, I just didn't explain. So often these quantum geometric quantities are given in terms of projectors instead of the wave functions.
Can I just ask also a quick question? So another way of getting those things more traditional, instead of using quantum geometry, is just to say that, of course, you have additional bands, and then you have some interaction, and this interaction is sufficiently strong to involve the other bands in the process. You have a self-energy correction when you project that, integrate out those bands, and you have self-energy corrections to the lower band, and that gives you an extra curvature. Those two things should be related. Have you guys found, compared the expressions that obtain this method and that, and that's exactly the same one?
Yeah,
Because
so
it looks like this can be obtained as an expansion of a generalized dispersion with the self-energy contributions coming in.
Yeah, so we have done many works where we project the whole Hamiltonian to the flat band, and there you see explicitly, for instance, that interactions, let's say on-site interactions in the whole space of bands, they lead into pair hopping terms in the flat band, for instance, or the band where you project. So I emphasize that superfluid weight is about a response and so on. So it's not just a pairing. This is how the Cooper pairs move. But indeed, one can get it by projecting the total Hamiltonian in the flat band, and then you have to look at all kind of pair hopping terms and others that give you transport. Okay, so so we then say, because we found this finite quantum geometry in the middle of the system, we wanted to compare this to this beautiful heavy fermion, topological heavy fermion model, which Andre and others have introduced for twisted bilayer graphene. And here we compare, this color scale is now quantum metric. So in this twisted bilayer graphene, the heavy fermions are to a large extent completely trivial quantum geometrically. They can be one-airized and so on. And then the big quantum geometry is here with the C electrons and around the gamma point and so on. Here in rhombohedral graphite, we also have biggest quantum geometry here at the rims, but this area where we have our heavy fermions, the flat band, that actually has a finite quantum geometry. So it's a kind of different type of heavy fermion system. And we think this is more general than rhombohedral graphite, could be for many other semi-metals too. And what this would mean in practice in this multi-layer rhombohedral graphite is that most of the superfluid weight goes into the bulk, inside the bulk. Sorry, the supercurrent goes in the bulk because it's this area where the surface states are hybridized with the bulk. But there would be also some surface supercurrent that is given by quantum geometry. So this might be interesting to observe maybe in some experiment. Okay, so how much do I have? 5. Yeah, okay. Right, so I can skip the last part maybe. But then about transport in flat bands. So I have talked a lot about supercurrent, but that's an equilibrium property. So one can also think about putting things in non-equilibrium, like having some channel and voltage there. And we looked at it in this work within a Keldysh formalism, in a toy model system like this. And here you see more details. So we have a system that can have flat and dispersive bands, and then some leads, and we calculate the current in the Keldysh formalism, and we can get both like any omega dependence there. So we can calculate the AC current in this kind of system with superconducting leads and finite voltage, and also the DC, and both of course with interactions in the channel or no interactions. And the funny thing that we found out is that, well, everything in dispersive states, they are always current. In flat bands, it's only the AC current in presence of interactions that shows up. So that's the supercurrent in that system. And what was a surprise to me is that the DC current in presence of interactions, which is the multiple Andreev reflections, it didn't happen. And that's funny because it's a coherent process. I thought it would happen, but apparently the flat bands really don't want quasi-particles to move, because of course also non-interacting particles don't move there. So it seems that quasi-particles are also suppressed, and therefore no multiple Andreev reflections. And then when we put one or both of the leads to normal, nothing goes through in the flat band. So in this simple model, it looks like that quasi-particle transport is simply quenched, so these flat bands could offer some kind of pure supercurrent. And this maybe is the case, because now in usual superconductors, both the quasi-particle and the Cooper pair motion, they are basically governed by the effective mass of the electron. But in a flat band, the supercurrent mechanism is very different from the electron motion itself. So this could be relevant for some devices, for instance. You can kill the quasi-particles. Now then we continued looking at transport, and now in a collaboration with Dima Efetov, so we have a theory paper and an experimental paper with a bit of theory added. And we looked at Josephson junctions in the theory paper, also in the general context, and then the experiment is TBG. So we wanted to see what happens to proximity-induced Josephson currents in this kind of SNS junction. And the usual story is that even if the middle part is normal, you can proximity induce superconductivity, some pairing potential that exponentially decays. And if you have an overlap, you will get the critical current, finite, exponential, and scale given by Fermi velocity. So again, seems curious, what will it be in a flat band where Fermi velocity is 0? So we started to look at this. And then we also thought that, okay, let's allow the flat band normal metals have some interactions. And then even if your proximity induced pair potential would be very short range, if you have interactions here, and they can be very small, this is not intrinsic superconductivity or anything, you can have much longer range than pair transport. So you can think about it that you induce first Cooper pairs because of proximity, and then these interactions help them to hop like they help in a superfluid wave. And indeed this happens. So we get an interaction-induced contribution to the supercurrent. I mean, this is always there, but people usually ignore it because the non-interacting part given by Fermi velocity is so much bigger. But in a flat band, this interaction thing could be important, and within a Ginzburg-Landau formalism, we can show that it's proportional to the quantum metric of the flat band. So here is a summary of what kind of behaviors we found. So as a function of the length of the flat band junction, if it's a non-interacting flat band, actually you don't get exponentially decaying proximity. It can just stop at some scale given by the quantum metric. But then in other scenarios, you might have this usual exponential decay, and the scale is given either by Fermi velocity, if your band still has some dispersion, or by nearby bands. So this is the gap to nearby bands. But if both of these scales are small, then it can be this interaction-induced quantum geometric current. So then a couple of words about the experiment. So this is a great experimental paper. It has many, many results. I just show one piece, one tiny piece here. So the system is a TBG, close to magic angle in this picture, but it's not intrinsically superconducting, while the leads are certainly superconducting. And then they measured the critical current, Josephson current. Here are the dispersive bands of TBG, and the flat bands are here in the middle. And usually in this kind of setups, the critical current is proportional to the normal state conductance, which is the case clearly here in the dispersive bands. But here in the middle, it's not systematic at all. You could have a minimum of Gn and maximum of critical current, or this kind of discrepancies. So something else is going on there, and we are suggesting that this interaction-induced flatband proximity thing is one possible explanation, and we did some kind of order of magnitude check by Ginzburg-Landau theory, taking the interaction scale from the known TC and some parameters of the system, and it seems reasonable. Good, so I think I will skip this, right? How many minutes do I? Yeah, stop. So I just stop, go over this and put here my conclusion slide. You can see what did I do, and my outlook is just I would like these things to be useful for going to higher temperatures in superconductivity. Thanks.
Okay, thanks Paivi for the questions. So we're open for questions. Please raise your hand and I'll give you the microphone.
So I was wondering, I think it's going to be a long question, but let me try to, how much of this you can translate to real space if I don't have a Brillouin zone? What comes to mind is bipartite quasi-crystals, like Penrose lattice and things like tiling and things like that. They have a flat band, or it's not a band, but you have a delta function at density of states, a macroscopic number. And if you look at the distribution in the lattice degrees of freedom, you see that there is a non-trivial structure depending on whether it's Penrose P1 or Penrose P2 or something like that. Of course, if I try to use the formalism of here, I'm not going to be able to, because I don't have lattice. I don't have momentum is not a good number. On the other hand, if you're just looking real space, you see that that's called flat band has a rich structure within real space. So I was just wondering if there have been thoughts or ideas of generalizing these to systems that don't have translation invariance, but they still can have non-trivial flat.
Yeah. So people have studied on this. First of all, these quantum geometric quantities you can express in real space as well. And people have looked at it, especially in a context of disordered superconductivity and so on. So they will be then something that describe the localization, like in real space. And so this certainly can be done. I would just say that it's not so developed yet as this momentum space.
Well, I'm taking a little bit to extend your talk by 1 minute. You had this wonderful line, superfluid weight 0 for Kagome Van Hoff nearest neighbor pairing. Can you comment quickly on this?
Okay, thanks, yeah, I can go. Yeah, this was a funny thing. Yeah, here. So in Kagome Van Hove singularity, if you have nearest neighbor interactions, you need to have a M pair density wave. This is kind of known thing from all these sublattice interference and so on. And we also, when we calculate pairing susceptibility, we get it for our interaction model. But then we calculate the superfluid weight, and it's actually 0. And this is actually an important message, that in these systems that have very non-trivial orbital structures and so on, you should not stop at the level of susceptibility, but also look at the superfluid weight. And we see it's 0, the ground potential is kind of flat, and we explain it by some Fermi surface arguments that with this pair, this momentum M, you can pair in this area, but if you tilt a little bit, you can pair in a larger area, so it's the same free energy, so it can somehow wobble.
So the net result at the end of the day is no superconductivity.
Yeah.
Does it mean that calculations of susceptibility has been done a little bit more accurately, and so then you will see that susceptibility actually does not diverge?
Probably, yeah. So our susceptibility was the simplest, but probably if you induce some kind of fluctuations there, you would end up with this as well.
Can I ask Paivi?
Yes.
In traditional BCS superconductors, we know the wave function. Every k is a superposition of nothing plus ck dagger, c minus
Yeah.
k dagger. And there's these coherence factors, which basically say that away from the Fermi energy, you have pure electrons and pure holes. Now here in this flat band with the interaction much stronger than the bandwidth, but delta much smaller than the bandwidth,
Yeah.
are we going to have a similar structure of U and V, or of the coherence factors?
They are constant basically in K.
They'll be constant,
Yeah.
so it's half-half,
Yeah.
or some...
So some numbers, but
that does not
constant
depend
in
on
K. Yeah.
Even if delta is much smaller than the bandwidth?
No. I mean, I meant in the ideal flat band.
Oh, no, perfectly flat band.
Yeah,
No,
yeah, then
fine.
they are constant.
Then I understand. But
Yeah.
if delta is much smaller than the bandwidth, but U is much larger, would that be a traditional BCS?
That's... It's hard to say. It might be something in between. Yeah.
You lose all K dependence at larger energies.
Yeah, but how would the ground state, let's say, look? That's what I was asking.
Technically BCS, I think.
Traditional BCS. Okay.
Any more questions? Okay, then let's 1, 2, 3. No? Okay. Let's thank Paivi again for the nice talk.
Thank you.
And I think we're going to have a coffee break.